Now it's on, yeah.
All right, so good morning, everybody, and so we're going to start, and this is Professor Cooper's last lecture.
Okay, thank you. Good morning, everyone. So, so last time I went through a couple of topics. One was the notion of Floquet topology, and I outlined how when we have a time periodic Hamiltonian, there is actually a richer topological classification than at equilibrium. There's some extra topological invariants that arise. And then I switched to discuss far from equilibrium dynamics, where there's no time periodicity of the Hamiltonian, there's no conserved quasi-energy, and but I discussed how one can still see that topology constrains the dynamics of the quantum many-body system. In particular, I explained how the Chern number of the state is preserved in time, at least up to times scale with the system size. I mentioned a nice idea about how one can use dynamical evolution of free fermion system to detect the topology of the Hamiltonian, that is the topology of the lowest band of the Hamiltonian after some quench. And then I moved on to start thinking about the dynamics of symmetry-protected topological phases. And I put up one board here that I mentioned last time, which was to really pose the question as to whether the topology of these symmetry-protected phases, the state is preserved under unitary time evolution, as it was in the case of number in 2 dimensions where there were no symmetries. And as I said, the interesting cases where we don't want to break the symmetries explicitly by causing the Hamiltonian to break the symmetries, so we assume that the Hamiltonian retains the symmetries at all times, and then you might think that if the symmetry is there, it's preserved by the Hamiltonian at all times. You might think that the symmetry of the state will be preserved under unitary. Cut out, has it? It's okay. But I said that it's not necessarily the case that these symmetries can be lost in the wave function under time evolution. So even if the symmetry is there initially in the wave function and the symmetry, the Hamiltonian you use preserves that symmetry at all times, it can be that the symmetry is lost in the wave function under time evolution. I give an example of the SSH model with a chiral symmetry, where I argued that if you switch the Hamiltonian under some quench from one Hamiltonian with chiral symmetry to another Hamiltonian with chiral symmetry, then the evolution of the states, the wave function, the evolution is such that the states no longer have that chiral symmetry. They depart away from the symmetric space. So today I'm going to go through that in more detail, formalize it a bit more, and explain how we've used that to develop a classification for non-equilibrium topological phases. And everything I'm going to talk about today is really the work of a former PhD student of mine, Max McGinley, who had a very successful period as a PhD student and derived many very interesting results, some of which I'm going to Okay, but before I get into this, I want to remind you about one particular feature of time reversal symmetry. So I want to remind you of how we describe time reversal symmetry. In quantum mechanics, because this is crucial to everything I'm going to say here. So let's just think about a spinless particle with some wave function psi r and t, which is evolving under some Hamiltonian h acting on psi r and t. And to represent time reversal symmetry, the time reversal operation on such a system involves an operation where we take time to minus time, and we transform the wave function by some operator, I'll call theta of t, acting on psi, and such that the equations of motion remain the same. And here, the time reversal for the spinless particle, this can be taken up to unit, well, you could use various unitary transformations, but we can take theta of t acting on psi to be the complex conjugation, the action of complex conjugation. And if you put these together into the time-dependent Schrodinger equation, you can show that under t goes to minus t, psi changing to psi star, you can show that this equation remains invariant provided the Hamiltonian is real, which essentially is the statement that there should be no there should be no magnetic field. This is a spinless particle, so magnetic field can only couple to position. So there's no orbital magnetic field because the magnetic field comes through in a vector potential which couples to momentum. And under this time reversal, you can see that it has the effects that you expect for on position and momentum, that the position will transform as the position operator theta t to the minus 1, which is just position, whereas the momentum will transform as, well, momentum is 1 over I d by dr, theta of t to minus 1, and this action of complex conjugation changes I to minus I, so this gives me minus p. So the time reversal is described by this transformation where the operator acting on phi can be taken as complex conjugation. So this has, well, there are extensions of this when we have spin and so on, but the key feature that I want to emphasize is that this transformation, theta of t, is anti-unitary. So where anti-unitary means that it's the action, if I take the inner product between, if I take the inner product, let me represent the inner product between two states as phi comma psi, and if I if I take the inner product between the two states which have been transformed by this operator, the symmetry operator, then if this is, in the usual case of a unitary transformation, we would say that this recovers the same inner product as before. But for the anti-unitary case, we get the complex conjugation of that inner product. So the inner product is preserved up to overall complex conjugation. Okay, so this is, which of course, this inner product, of course, is the complex conjugation of what we had before. And this anti-unitary symmetry is actually what's crucial and what underlies the situation in which the symmetries can be lost. Okay, and you can summarize everything I'm going to say here about these dynamics to say that one has to be careful when dealing with anti-unitary symmetries. Okay, so I'll with that, well, to make that explicit, let me now write that out, and describe what we mean by dynamically induced symmetry breaking. So this is something we thought about a few years ago and motivated by these sorts of issues of quenches of symmetry-protected topological. So let's imagine that we will make a quench. I will say that initial Hamiltonian, let's say, has some symmetry or some set of symmetries. And so if I want to work in a full second quantized notation rather than just Hamiltonian matrices, which we have been thinking about for single particle states. So here I want to think in a full second quantized notation, and the reason being that it's convenient because all symmetry operations we can write as connected to operators that commute with the Hamiltonian. In the sort of tenfold way classification of particle hole symmetry, chiral symmetry, and so on, there are these relations about how the Hamiltonian transforms to minus itself or minus the complex conjugate of itself, and so on under certain transformations. Here in the second quantized picture, we can just summarize saying that the Hamiltonian commutes with some symmetry operator. And so let's say initially we have the system in the state of the Hamiltonian, so it's a simultaneous eigenstate of the symmetry operator. Okay? So the initial state has the symmetry of the symmetries of the Hamiltonian. Okay? But now we quench to some final Hamiltonian, and we're going to require that the final Hamiltonian also commutes with the symmetry operation. Okay, that's as I said in posing the problem. But what you can quickly see, it's very straightforward to see that if you look at the action of this operator on the time-evolving many-body state, it's no longer an eigenstate because O e to the minus I hft. Okay, this is the time-evolved state. So I act with the operator, but this is not the same. Well, we can't just say it's an eigenstate. This is not the same as e to the minus I hft O psi I, because O, although it commutes with HF, if it's anti-unitary, it doesn't commute with I, because the action, anti-unitary operator around the I changes I to minus I, because it acts like a complex conjugation. So it's not equal to that for anti-unitary symmetries. And so that's essentially, in a nutshell, that explains why, in the example I gave before, there was we had the quench where we retained the symmetry of the Hamiltonian, but the state didn't retain that symmetry. It didn't remain an eigenstate of the symmetry operation. So with that idea in mind, we developed a way in which one can classify the topology of these non-equilibrium quantum systems. So I just want to sketch the rationale here, or how one can define this. So I have a topological classification of out of equilibrium. I just remind you that at equilibrium, one way to think about the topological classification is in terms of adiabatic continuity. Under some variation of the Hamiltonian, but retaining the symmetries, symmetry H of some parameters that we are allowed to vary slowly, without gap closure. So that to be adiabatic, and to stay in a topological phase, we need the gap to remain open, so without gap closure. And then we had this sort of picture of, different regions of Hilbert space, which were different topological sectors, which we could adiabatically, within this sector, all states were connected in this adiabatic manner. Now, we can extend this to an out of equilibrium, a notion of topology and out of equilibrium systems by replacing adiabatic continuity unitary time evolution. So we have connected by unitary evolution, again, under symmetry preserving Hamiltonians, which are, depend on time in some way, but they're always symmetry preserving. Here, I'll put hats on this side. I'm trying to use hat whenever I really mean full many-body Hamiltonian in second quantized form. So that's I'll use that more today than previously. Okay, so we under symmetry preserving Hamiltonian. Now, the notion of closure, what we need to do is to say that the entanglement should remain of finite range or short range or finite range, and essentially that's means that we should do this for finite time and not let the time go far enough that information can spread to the boundaries. Again, I said before, if you wait very long and all information can spread all the way to the system, then the notion of dimensionality is lost. So this here we have under symmetry preserving Hamiltonians for finite time. And this is to maintain range of entanglement. Okay, and then well, this of course is adiabatic continuity is a subset of this. So this introduces extra deformations that you couldn't do adiabatically because you can have non-adiabatic processes. So in general, but again, we have some classification of A prime, B prime. But typically, this is going to be some subset of these. Some of these can get joined together. But we have a well-defined notion for connectivity of different states, and we can use that to classify topological phases. And one characteristic that one can always use to distinguish these is this entanglement spectrum. As I said before, remember here we could think about these are ground states, and you can think about the true excitations of the physical edge of the system and have gapless edge states. But you can also just take entanglement cuts and look at the wave function and see that the wave function has gapless modes or not. In the same way, here we're far from equilibrium. These aren't the ground states of anything, or any natural Hamiltonian, so we can't think about the actual physical edge excitations, but we can still take entanglement cuts and characterize these by their entanglement spectrums. Okay, so let me, so we use this to develop or to find out what the non-equilibrium classifications are, both for non-interacting and interacting symmetry-protected topological phases. I don't want to go through those classifications. One can find those in the literature, but I just want to say, give some insight into what emerges. So I'll think about the free fermion case. So this is the Altland-Zernbar classification, the 10-fold way of classifying free fermion systems. And in the class with no symmetry, so-called class A, no symmetry in 2 dimensions. So this is the class that gives you the Chern number. At equilibrium, we get a set of integers, the Chern number, which this breaks into spaces labeled by the Chern number, and out of equilibrium, it remains the Chern number. So the statement that I said last time, that the Chern number is preserved out of equilibrium, is a statement that the structure is the same under adiabatic or unitary evolution in time. Okay, if there's no symmetry, that's just that the Chern number is really preserved dynamically. But in the other case, yeah.
Sorry, yeah, there was a question in the chat.
Oh, please.
You can.
Yeah. So why can't? Yeah. So okay. Thank you. So the question is: so why can't? So if I've got I have an operator O. If this operator is anti-unitary, then it involves, it can be some unitary operator times a complex conjugation. So it has to involve this action of complex conjugation, which is what leads to the fact that the inner product becomes its complex conjugate under its action. So let's just think of this anti-unitary operator as being complex conjugation. And the issue is the action of it on the square root of -1 on I. So if I have O times I, this is the same as -I times O. Okay? Because because if I take the complex conjugate of everything to the right of this, then I have to change the sign of I, and so if I swap this order, I'll have to account for the fact that the I would have changed sign under the action of O. So this means that O does not commute with the square root of -1. Okay? And so that's why whenever I had e to the minus I ht, and I asked, what's the commutator of this? It's not 0 because of this fact. Really, I could be more explicit and say that O e to the minus I ht is really e to the plus I ht times O, because here, using the fact that provided the Hamiltonian commutes with O, then the only thing that changes when I take this through is that the I goes from I to minus I. O commutes with H, so there's no problem about this being an operator, and we can write it this way. Okay? Thanks. Okay. So the other case I've discussed is for the SSH model, and that's a class that is so-called BDI, which has got it has time reversal, squares to +1, charge conjugation or particle hole symmetry, and chiral symmetry. So it has more than just chiral symmetry. So it's actually this class BDI in one dimension. I haven't explained any of these in the lectures, and I don't intend to, but I'm just writing it down for if you go and look at the tables and want to see where things fit. This is where it would be. And at equilibrium, so this is the equilibrium classification, and this is the non-equilibrium classification that Max worked out. So here, this Z becomes Z2. So before we had all states which had different winding numbers, which couldn't be connected under adiabatic evolution without gap closure. It turns out that they can, out of equilibrium, those all collapse to just two classes, Z2, either 0 or 1. There are two classes that can't be interconnected, but clearly, out of equilibrium, it means that there's a whole subset of these that collapse into the same topological sector, and another subset that collapse into the other. And effectively, it's the even winding numbers that all collapse to being equivalent to 0, and the odd winding numbers all collapse to being equivalent to 1. Now, there are other classes as well. There are superconducting classes. There's the Kitaev wire, which is the famous case of a spinless, spin-polarized superconductor in one dimension where there's a Majorana fermion at the end. That gives a Z2 classification at equilibrium. Out of equilibrium, it's also Z2. So there's no loss of that topological phase or that topological classification out of equilibrium, but there are other ones that are lost. And essentially, it comes down to whether there are anti-unitary symmetries that are stabilizing. Okay, so I want to, in the time remaining, I want to go through some of the discussion of some of the physical consequences. Okay, so. Or what are the consequences of this, of knowing this out of equilibrium classification? So, well, the first one I've already alluded to, which is the wave function topology, whether or not wave function topology can be changed dynamically by doing something non-adiabatic. You know, so if, let's say we've got a Hamiltonian, or a Hamiltonian is restricted to being in a certain symmetry class, is there some way in which we can time evolve the Hamiltonian, make some non-adiabatic process that changes the wave function topology from one topological sector to another, that is one equilibrium topological sector to another. And we've said it for 2D Chern number, there's nothing you can do. The Chern number is preserved, you're stuck. But for this SSH model, you can. Okay, we can change it by even integers. So this is about wave function, or many-body wave function topology. And so I want to, in discussing these, I want to go, fairly in some detail through these sort of simple examples. And my simple examples are going to be, I'll base it on this SSH model, just so that we have a standard, a simple picture in mind. So remember, we had this couplings, J prime and J, and we had our Hamiltonian, single particle Hamiltonian, H of Q dot sigma, with Hx plus I, Hy is J prime plus J e to the I Q, okay? And so I want to give one simple example for how we can change the wave function topology in this case. So let's imagine this is what all we can do, J and J prime nearest neighbor coupling, and let's say we start initially in a topologically trivial case where J, we take the ground state where J is 0 and J prime is non-zero. Okay, so that's just dimerize in between the AB, make this AB bond strong, and these other ones 0. Okay, so then the wave functions at initial time are all simple. It's actually it's just they're all in the x direction. They're all the same. 1 over root 2, 1, 1. So and this has got no winding number. Like there's just no variation of the block wave function with wave vector q. So it's there's no it's as trivial a band as one can consider. But now we quench to a Hamiltonian where we flip this. So we have J non-zero and J prime equal to 0. So we switch off this bond and just turn on these bonds. And then it's straightforward to write down what the wave function is as a function of time. It's e to the minus it times the Hamiltonian. The Hamiltonian is, we get jt. I only have this j e to the iq, which is cos q plus I sine q, and this becomes cos q minus sine, cos q times sigma x minus sine q sigma y, acting on the initial state, which is 1 over 2, 1, 1. And of course, one can do the algebra to work out what the state is. Let's not go through the algebra, but I'll just write it down. Well, it's evolving in time in some in some fairly simple sort of way, but there are certain special times. This is a very simple Hamiltonian. It has flat bands and perfectly repeating, perfectly periodic oscillations of the states, and there are certain times where this gives you simple results. Now, in general, we started with something which had chiral symmetry, which meant that on the block sphere, the state was described by states that sit in the equatorial plane. Here, they were all the same state, just a point on that. As a function of time, it starts to wander away from the equatorial plane, but there are certain times when it comes back to something very simple, and in particular, this is whenever t star times j is pi over 2, then you find that UQ of T star gets the chiral symmetry back, and it takes this form, e to the minus IQ. Okay. So the picture, well, just to draw a picture of what I've been trying to say in words, at T equals 0, the state was that everything was in the X, the Sx, sigma X eigenstate, this UQ at T equals 0. At non-zero, then what happens is that this starts to, as a function of Q, this starts to trace out something like a figure of 8, where it's not lying in the equatorial. I'm not sure how clear my drawing is, but this is meant to represent the U of Q is now some set of vectors that are now not lying in the equatorial plane, but starting to come up into the upper hemisphere, then they loop back down, and then go into the lower hemisphere, and then back up here. So it's periodic in Q, changing by 2 pi. And this time T star, this is a simple enough system that actually, magically, this figure of 8 collapses onto just being on the equator, and it wraps around the equator twice. So at T star, the chiral symmetry of the state is restored, but now the winding number, it winds twice around the equator. Here, the winding number was 0, it didn't wind at all. So this is consistent with this classification that the equilibrium set of winding numbers are reduced to just the set Z2, because here 0 is equivalent to 2, and so on. Okay, let me, where should I go? So that was, one consequence. Another relates to the entanglement spectrum. Now, typically, if we have something like this where the topological classification is reduced out of equilibrium, then typically what that means is that the if you start in some topological phase with some entanglement degeneracies, then typically at later times those entanglement degeneracies will be lost. And so here, so that's readily demonstrated. Here in the example, I'm using this example that I just discussed also to talk about entanglement degeneracies, but actually this is a rather special one where we started with something that had no topology, and there was a special time at which the topology gets restored and we find entanglement degeneracies. But let's just see how that goes. So this is, again, a particularly simple model chosen just to illustrate the physics. So initially at T equals 0, whenever we had strong bond J prime and J was 0, then we only have these bonds here. And so the ground state, as described by this sigma X eigenstate at all values of Q, the ground state is that we have a delocalized, one delocalized fermion between each of these pairs, okay? And so here, initially, if we take an entanglement cut, then, well, it's separable, so there's no entanglement. So the set of eigenvalues of the density operator, of the reduced density operator, so which I introduced last time, is the set of, well, it has one and then everything else is a 0, okay, because it's perfectly separable. But at this point, t equals t star, where this symmetry is restored, that's a special point where, you know, what we did was we had this coherent superposition of a fermion between A and B. Then we turned off this coupling and we introduced coupling B to A, and essentially what it does is it transfers the particle. At this time, the particle gets transferred to its nearest neighbor. So this delocalization or this entanglement of the fermion between the A and the B site now gets expanded out over a larger distance. And the picture in this case is that, you know, well, here, you know, while we're forming this state, there's a bond J prime that's switched on, A, B, and so on. And the picture is that this sort of bracket that shows the delocalized fermion involves this A going to some B over here. This B is entangled with that A, this B with an A over there, and so on. Okay, so this, yeah, this one, essentially this delocalized fermion now gets transferred to being between B and A, which is what I'm representing here. And so now, if we take an entanglement cut, so our entanglement cut between, you know, again, in a unit cell between B and A, it cuts two of these, and then it's a straightforward to show that the eigenvalues, well, let me write it down here, e to the minus xi A, is, well, there are two delocalized fermions. Each of those gives you a degeneracy of 2, so there's a fourfold degeneracy. So you get a quarter, a quarter, a quarter, a quarter, and then 0, everything else. Okay. Okay, so this you see the change in topology from the change in the entanglement spectrum. It's, as I said at the start, it's a peculiar case because actually it's very fine-tuned that you actually go, you get back into the, this model is simple enough that you get back into the chiral metric state with a larger winding number and therefore with more degeneracies appearing. Typically, what will happen for generic systems, for example, interacting systems, is that the degeneracies you have will be lost. Okay. And one other consequence that I want to discuss is to do with the decoherence of edge states. So this is everything I discussed so far. The first two consequences are bulk consequences. So they're properties of the bulk wave function. But now I want to talk about what this classification means for edge states or surface states. And essentially the way to think about it is that if we have, you know, our equilibrium topological system, we know can have some topologically protected surface states. Now, if it's in a class where the non-equilibrium classification is reduced, then those surface states can start to decohere. They can be lost once you drive the system away from equilibrium. And so you're not in the ground state, but you're in some excited state. And the way we thought about this is to impose some symmetry preserving noise. So imagine that the system is in some environment where there's some symmetry preserving noise that acts on it. So that means there's some, some coupling V of t, which is depending in a noisy manner, so that it causes the system to be driven away from the ground state. Then this symmetry preserving noise can induce a decoherence of the gapless surface states. And there's an example of this that was known in the literature, which was from Stern and Flensburg, where they discussed a time reversal symmetric topological superconductor where there were Kramer's degenerate, so it's time reversal degenerate Majorana pairs, and they showed that if you have a time varying system, like you change couplings in time in some adiabatic manner, then that will cause a mixing of those states and a decoherence of the supposed quantum register that you might try and make out of those surface states. So this is the same physics arises here, and you can understand their result in terms of this non-equilibrium classification. Here, sticking to my attempt to be pedagogical, I want to present things within the SSH model. And here, because in the SSH model, we had this classification that the Z went down to Z2. If we have a single edge state or a single edge mode, that's of classification of 1, that's still preserved out of equilibrium. So in order to lose the symmetry preserved, to lose the symmetry imposed topology, we need to start from a state which has got 2 gapless edge states, right? Because 2 goes to is the same as 0 in a Z2 classification, and so if I've got 2 edge states, then noise can cause those states to decohere. So here I'm going to take it's a slightly artificial model from from the physical perspective, but I want to do it because it's a bit more, well, just to connect to what I've been saying so far, rather than having to start talking about Kitaev wires. So we're going to start from a state with an even number of edge states. So we'll get decoherence for an even number of edge states. So, to see that, we need to come up with a model that has an even number of edge states. The SSH model actually can only give you 1. So to get a model that will give us 2 edge states that's of the same spirit, we have to consider a sort of extended version of SSH. So we have an extended version of the SSH model, which has a ground state with winding number 2 as a ground state. So it's going to be the same. Its state is going to be of the form of the state that we considered making dynamically in this case. Here we made it dynamically just with nearest neighbor couplings. To make this to establish this as instead of Hamiltonian, we actually have to put in longer range couplings between these points B and A. They still preserve chiral symmetry. It's off diagonal in this site basis, but they have longer range than what we had before. So we basically, I could reuse this diagram and say that we're going to have A, B, A, B, A, B, and so on, where we have our couplings J prime, coupling J, this was J prime, J prime, but then we also put in couplings like this one, which let's call it K, and then, well, they continue okay, so all B's are also coupled to A's that are further away. Okay. So the Hamiltonian is what I had before, but now hx plus I hy is j prime plus j e to the I q plus k e to the 2iq. So coming from the fact that it couples unit cells that are separated by 2 lattice constants. And so if we consider, well, we can make the fizz, but it's helpful to, just for to see the edge states, it's helpful just to set the j and j prime equal to 0. So, and let's have a system with a boundary. So there's really a boundary here, and then we'll have A, B, A, B, A, B. And so with j and j prime set to 0, well, if that's the case, if this is the first A, the j prime, or this A is not coupled to anything, this B site is coupled to an A over there by K. This A is also coupled to anything because it only be coupled to a B here, but that's not there when there's an edge. And then this B is coupled, and everything else is coupled. But there are two states here which are decoupled. So in this limit, which is within that topological phase, we can imagine taking j and j prime to 0, keeping the gap open in that n equals 2, n winding 2 phase. These are the two gapless states are just located on these two decoupled sites. So I think I'll say a couple more words about this and then take a break. But just to what we're going to do is we're going to imagine that we introduce, we have a noisy environment, V of t, which, for example, which is going to modulate these couplings j and j prime. So we might start with something like this, and then introduce j and j prime, which are time dependent, which come from some external noise, some external modulation, and what I'm going to show is that this will cause decoherence in the sector of the states defined by these two gapless edge modes. Okay, so these are couplings that retain this chiral symmetry, but it's going to cause decoherence. But just to present that, I'll take I can understand it all actually just by considering these. Just by considering 4 coupled sites. Here there's another coupling K. All of these sites, B and this one and so on, I can imagine just eliminating them by having couplings K that are so big, K prime, that are so big that the energy gap to change the nature of the states on these sites is very large. And so I only need to keep these 4 states in order to demonstrate the effect. So that's what I'm going to do. I'm going to have a model, which I'll discuss in detail when we get back after the break, where I just keep these 4 sites, and I'm going to introduce j prime of t and j of t. And since this is just 4 states, I can write out the Hamiltonian for this at any given time. H of t is given by, well, I'll label these 1, 2, 3, 4 in the site labels here. Then I'll get A is coupled to B with j prime, but it's not coupled to anything else. So here, and this is j prime. 0, 0. B is coupled there. It's coupled to, it all retains chiral symmetry, so nothing's going to be coupled to itself. So B is coupled to A, the 4th one by K, and it's coupled to this by J. So J, K, and then this A is just coupled to B and not coupled to anything else. Okay? So you can write down the matrix for this. And it's a straightforward exercise, or you can to show that you get 2 zero-energy states, which are the states psi1 proportional to 1, 0, 0 minus j prime over k, and psi2, which is 0, 0, 1 minus j over k. So these are the two states where when I decoupled it, I only had amplitude on the first A site or amplitude on the second A site, which is the entry in the third position here. But if we turn on these couplings, then because they preserve the chiral symmetry, they can't possibly change this energy away from 0. So these two states are topologically protected because our Hamiltonian has the chiral symmetry. They're topologically protected to be at E equals 0. Okay. But what I'm going to show is that once we start accounting for the fact that these can vary in time, then that time variation will cause mixing and decoherence of these. Okay, but I think I'll stop here and come back to that dynamical aspect after the break. I'm happy to take questions if there are any.
Okay, so other questions?
Can I ask a question?
Yeah, sure.
About the SSH, you say that it's in the BDI class.
Yes.
But that means that you are imposing a set of symmetries because, like, given the chain as you describe it, it doesn't necessarily contain all those symmetries, or you can, like, choose to enforce different kinds of symmetries.
Yes. So one. I think that the chains that I've written down do have those symmetries in that. So it's that if we just have these couplings which are, off diagonal in this site basis, in this AB basis, and there are no. Well, okay. Now I've introduced this K. In principle, I could break time reversal symmetry by putting a phase on this and having a closed loop where there's a net flux picked up as we run around this phase. So indeed, you're right that I'm assuming here that K, all of the couplings are real, so that I'm not going to break time reversal symmetry. So it's true that one has to be more clear about what, if you say that the system has a certain symmetry, you also have to say what range of parameters you're allowing in the model. And here I'm assuming that time reversal and particle hole are also, the couplings preserve those. But indeed, I think that now that I've got this longer range loop, in principle I could.
But again, I have an announcement. The discussion session of tomorrow will take place after the lecture at noon. Okay, not in the afternoon. Okay. So after the last lecture by Valentina, tomorrow we have a discussion session. Okay, not. So we have the free. Okay, please.
Okay, welcome back. So so I had set up that there are these exact zero energy states if we introduce in a static way. If we've got J and J prime or any perturbations that are or any couplings that preserve chiral symmetry, you must have two states which are exactly zero energy. Here, I call them psi1 and psi2. They're not orthogonal, so I'm going to put tildes on these because I want to work with the orthogonalized versions of those, but which of course we can find. But if I think of J and J prime as small, then actually we can also neglect the difference for much of what I say. So so the way I want to think about the mixing is to just consider the adiabatic evolution. We're going to make the couplings J and J prime vary in time. They're not static, but now they vary in time. But I want to think about them varying slowly in time, slow compared to the gap, which is basically set by this coupling K. And then we've got some parameter, lambda, which is varying slowly in time, which is has got these two components, J of t and J prime of t. And we can understand the evolution in this degenerate space using the notions of non-abelian Berry connection, beautifully presented by Wilczek and Z in the early 80s. So there, we have some Hamiltonian, their general formalism. We have some Hamiltonian that depends on some parameters, lambda of t. There's some set of zero modes, so the Hamiltonian acting on these is zero, like this psi1 and psi2 that I had here. So these are, this is, if we consider the thing, for the static, zero modes. Okay. And they write, as the full time evolution, the full wave function, psi sub I, if we start in a state psi I, little psi I, the full time evolution, so this is the instantaneous, or sort of instantaneous, I should say, instantaneous. Okay, so if I just work with h of t, we can find these for a given value of this. But now we think about the dynamics where we start in state I at time t equals 0 and ask how it evolves in time, and they write it as some unitary operation expanded in this basis. So a sum over J, so it's expanded in this basis of instantaneous eigenstates, zero energy eigenstates, with some matrix, unitary matrix Ui J of T. And this takes the general form. This matrix U of T is the time-ordered exponential of minus I, the integral from 0 to T of some A dot d lambda. This is now the matrix, where the matrix A, the ij entry, is the matrix version of the Berry connection, d by d lambda of psi I. Okay, so this is the non-abelian Berry connection. It means that we can trace out the evolution just by thinking about paths in parameter space as before. So let's think, in our setup, imagine that we have, we've got J prime of T, and imagine that these are fluctuating in time in some way, and we can just compute, we can compute something where it fluctuates by something of order J0 and does a loop in parameter space. And if you do this and work through the algebra to compute this vector potential in the basis I stated before, you can find that the integral, the integral of this matrix around the parameter space is of order J, some scale J0, the size, let's call this J0, it's the area J0, J0 prime over K squared, times something which is it's actually the Y Pauli matrix. So it's, what that means is that we get mixing, right? Whatever state we start in, if this were the identity matrix, then we wouldn't have had any decoherence. We'd have started in a state which is a particular superposition of psi1 and psi2, and we would stay in that state at all times. But actually, if we have loops and fluctuations that cause loops in this parameter space, then that actually gives rise to evolution, which acts as in a non-trivial way on this degenerate subspace. And so this shows us that this noise in J and J prime leads to decoherence or mixing of the topologically protected surface states. Now, if that this is something which only, if we make a system with a bigger and bigger gap, let's say take k bigger and bigger, which causes the gap to get bigger, this only falls like a power law in the gap. It falls like k squared. So it's something that can be suppressed if the gap is big enough, but it's only suppressed as a power law, not as some exponent in the gap, which is what one typically looks for a topological system. Okay, so are there any questions on this? I'm going to go on for the last part of the lecture to talk about an open quantum systems and to make what I've described here to that setting.
I have a question. How do you know that this phase is topological?
Which phase?
Yes, it's A. This non-abelian Berry you constructed.
Yeah, no. This has no. There's nothing.
Topological means that it's a flat connection. So in principle, it doesn't depend on the path. The contour does not depend on the path you do it, but in parameter space. But how do we know that this is? When you have a loop, okay?
Yeah.
You have a loop. The fact that it's flat means that it doesn't depend on the shape of the loop. The integral does not depend on the shape of the loop.
Yes.
So if it is closed, then that's it. Okay. But this is a typical thing of a Berry phase. But here, is that clear that? It doesn't matter for the result, but for calling it a Berry phase, it has to be a flat connection.
So I need to look at back at the
could be a dynamical phase of any kind. So you see, not the Berry phase.
Okay, I need to.
In the end, it's a semantic question.
Yeah, so I need to look again at this. Wilczek and Z has this paper from '84, and I was lifting the notation from there, but I need to. I lifted only what I needed to make the point I want. So I need to.
So Wilczek said. So probably.
No, I just.
Okay. Thank you.
Okay, but thanks for the question. Okay, so yeah.
Sorry. Also, probably very stupid question, but I don't understand the role of the bulk actually. Why couldn't you just make a very similar argument just with the two orbitals A you started with?
The two. Well, I needed some. I needed these states to change in some way, that through this coupling J prime. So I have a special situation where there are two states. I'm changing the Hamiltonian, but leaving an exact degeneracy. If I only had a 2x2 matrix, and I wanted to get two zero modes, then the matrix has to be 0. I don't have any more parameters. So I need I need this. I think in this case, it's the minimal size system I need in order to have a chiral symmetry. So it has plus E minus E symmetry. There are two states pinned at 0, and then there are two states which are not at 0. And it's the mixing with those gapped states that are not at 0, and that adiabatic evolution that's causing the two states at 0 to be mixed with each other. So I needed some freedom to go to these to be able to do anything and not just have a 0 Hamiltonian. Yeah. Thanks.
Okay. Other questions?
Okay. So the last thing part I want to talk about is open quantum systems, and there's much that one could say there, but I'm going to focus just on a question that Max and I addressed, motivated by thinking of this type, that here, here we understood that there can be decoherence once you have a coupling to noise. Even if the noise preserves the symmetries, it instantaneously it preserves the symmetries. Those symmetries are lost, and you get decoherence of the edge states. Now, there's a way in which that's that you can understand that in simple terms, that the noise itself, even if it's on time average, the noise the noise spectrum is such that there's no no periodic change in the amplitude of the noise in time. Actually, any realization of the noise by itself breaks time reversal symmetry, because this time dependence is, the fact that we have some fluctuation which makes us go around in a loop in the anti-clockwise way. That's coming from time reversal breaking by the environment itself. So we wanted to think about a situation where we hadn't explicitly broken time reversal symmetry by the time evolution of some external noise, and but we couple the system to the environment, and for that we wanted to think about open quantum systems. So that's the next part, and the last part is to say some words about how this extends to open quantum systems. Okay, so this was... Okay, so I have in mind, some system, S, some quantum system, which is coupled to an environment. And we know that once we do that, the entire system is now this combination of these two. If I just make measurements on the system itself, then I have to replace the description of it, not in terms of a state, but in terms of a density operator in general, and some master equation. And this arises because if we start with some separated state or separable state, then generally this coupling leads to entanglement. And an increase in entropy. For the system S. And of course, one can, in principle, imagine looking at situations where you put other reservoirs or other environments on, and the system could be out of equilibrium. It could be that it's not really an equilibrium system, but you've got a difference in chemical potential or something, and you want to study the properties of that. Now, there's much that one could say here, but what I want to do today is just restrict to the situation connected to what I just discussed, which is the fate, to ask about what is the fate of the symmetry protected surface states. Once we take our system and couple it to some environment. And the result that I want to describe is one that's quite natural, but one that one can demonstrate very generally, which is that these surface states are typically fragile. They will decohere if they are protected by time reversal symmetry, or more generally, if they're protected by an anti-unitary symmetry. So this is, time reversal symmetry protected states typically are fragile and decohere. And this is connected to what I just said for the noise case, but these here, loosely speaking, one can understand that what's happening is that these anti-unitary symmetries or time reversal are being broken by the coupling to the environment, much as the fact that you couple to an environment can give rise to the growth of entropy in the system, that which itself is a signature of broken time reversal symmetry. The system itself here will lose its symmetry-protected surface states generically once we have this environment coupled to it. Okay, so that's what I want to sketch in the remaining half hour or so, and to discuss it, we have to be careful to deal with symmetries. Of course, we have to set things up and explain how symmetries act and how symmetries constrain the dynamics. So we're going to imagine that we have a system has a symmetry that supports some SP symmetry-protected topological edge states. So let's again, working in second quantized notation, the Hamiltonian of the system commutes with some symmetry operator, or some set of symmetry operators. And just to make everything consistent in today's lectures, I'll imagine for discussions here, not the case we discussed in the paper, but connected to what was described, where we have these this extended SSH type model. Well, let me say this is the drawing the end where there were two surface states. So this is e.g. this is extended SSH with two surface states. And now, in this case, so there I had these states psi1, some orbitals psi1 and psi2. Here, I'm going to think. It's more helpful to think in some second quantized way, where if I've got these two orbitals, then I can think of the occupation of the system as having, well, some filled band of the bulk states, and then there are these two states, two fermionic levels. Or two levels exactly at zero energy, which we can choose to occupy or not. And so these two surface states will give rise to four possible states, where they're both empty, where the first one's occupied and the second not, or I have 0, 1, or where they're both occupied. And of course, these are sectors of different particle number here. The particle number is 1, 0, 1, or 2 in this zero energy sector. So what we'll think about is the case of this n equals 1 sector. And we'll call these two states up and down. Okay, they're just two degenerate, topologically protected degenerate many-body states. Are distinguished by the whether the fermions occupying one or other of these two degenerate single particle states. Okay, so we could, if we want, we could say that there's some qubit, which is the state of the system, which is some superposition of this up and down. Okay. And the question is, does it decohere? When coupled to the environment. Okay, so but here, as I said, need to think about how it couples and symmetries. So it was supported by some, in this case, chiral symmetry, but we couple it to an environment, and as before, if the environment broke that symmetry, then all bets are off. Of course, it will decohere. So we want the environment to preserve the symmetry. So we'll consider the case where the symmetry operator commutes not just with HS, but also with the system-environment coupling and with the environment Hamiltonian. So it commutes with everything. So that's saying that the symmetry is preserved by the universe. And we'll even consider the strongest possible case, which is that we can always write any coupling between two subsystems, the system and the environment, we can write as a sum over operators, some operators S alpha that act only on the system, and some operators E alpha that act only on the environment, where these operators are Hermitian. So there's some observables that act on the system, some observables acting on the environment, or coupling is of this form, and our strongest, the symmetry requirement that we're going to impose is that the operator O commutes not just with this product, HSE, but it commutes individually with S alpha and with E alpha. Okay. So this is a much stronger symmetry requirement than one might ordinarily require. For example, if the symmetry was to do with the U1 symmetry of charge conservation, then saying that transformation commuted with the system environment Hamiltonian would be to say that the charge is conserved in the entire system, but saying that it commutes separately with the system operators and with the environment says that the charge on the system is conserved and the charge on the environment is conserved. Okay? So this factorization and the strong symmetry requirement is really saying not just that we have a sort of globally conserved symmetry, but it's conserved, it's both on the system and on the environment. Okay. So we're going to impose that. And what we're going to, I'll just state what the result is. The result is that if this symmetry is a unitary symmetry, then there will not be decoherence. But if this symmetry is anti-unitary, then generically it will give rise to decoherence. Okay? So that's the, and maybe I should just, in case I don't get to say it clearly at the end, essentially where the difference arises is that what I've done here, if separating into two parts, is something that is not strictly valid once we have an anti-unitary symmetry. About time reversal or complex conjugation, we can't really think about that as acting separately on the system and separately on the environment. I mean, we can write down operators which are time reversal symmetric. So if we think about typical observables that are time reversal symmetric are like charge density or energy density and so on. But operators that are time reversal odd are things like spin density or current or something which is clearly time reversal odd. And so we can very naturally classify our Hamiltonians as things which are, say, charge density coupling to charge density, and say that looks like it's got time reversal symmetry, both acting on the operators acting on the system and the operators acting on the environment. That's perfectly valid and very clearly defined. However, the message that I want to get across here is that the fact that you can do that at this level of the coupling is not a precise statement for the subsequent time evolution. Actually, the entanglement between the two systems means that you can generate terms which effectively break time reversal on the system. So I'm going to try and explain that in a few lines of algebra, but I just thought I should maybe flag it up here that this is the point where, in a way, I'm cheating you, or where a difference emerges that we can't really think of time reversal as applying just, or these anti-unitary symmetries as applying just to one system or the other. Whereas for unitary symmetries, we certainly can. Charge, we can define within a subsystem. Okay, so let me.
I'm sorry.
Yes, please.
Can't you simply say that anti-unitary operator is just a unitary operator times charge conjugation, and then discuss the unitary part? So
No.
call K the
Yes.
and the complex conjugation.
Yeah,
Then
so I can separate, yes, so I can
separate.
I can separate that, but that K is always there, and that makes it,
K
that's,
is global, yes.
it's, and that, the global part, yeah, it's the global part that is, that means that we'll get decoherence. And you'll see it, I mean, it comes down to something very simple, so I want to try and explain, show how you see it. So in fact, this, I said that you can kind of think of this as being like breaking of time reversal because you've coupled to an environment and there's entropy growth and so on, but actually you can show it in a very simple way just by using this anti-unitary property. So that's what I want to try and say. Okay, so take a simple model. So just to get the key ideas and to show how you can get it. So let's take a simple model where the environment has got no dynamics. So this is a bit sick, but it shows us, we can put it back in, but it shows you where the terms come and where the difference arises. And we have initially, that, at initial time, the total wave function of the system is the system one, which is some qubit state, whatever we have here, and something in the environment. Okay. So here I'm going to work in the wave function prescription and really track how the entanglement grows and how the two systems get coupled together. Okay. Of course, we can, once we understand this, you can put it back into some master equation approach, but it's here we're really deriving what the allowed couplings can be in that master equation dynamics. Okay, so let's think about time evolution and just do it to first order perturbation theory. Okay, so we just act with e to the minus I ht. H is H system plus, but H system acting on psi gives 0, right? Because these are 0 modes. So, and then there's H system environment, which is this S alpha and environment E alpha. So to first order, we just expand to first order that exponent, and it's equal to, well, we have what we psi s phi e minus it sum over alpha. I'm going to write projection on the ground state S alpha projection. Just for convenience, I'm going to put these projectors onto the ground state. So this this projector is just projects onto the sector of interest. So I'm neglecting the small amplitude to be to end up in some rapidly oscillating state at high energy. So I'm just looking at the ground state evolution, or the low energy part of the wave function, and so I take the action of this and I project onto the ground state. So I have this operator acting on psi, but this is straightforward to show. I won't do it here, but it's straightforward to show that because this observable, this Hermitian operator S alpha, sorry, these are all many-body. Because it commutes with the Hamiltonian, right? We've got this strong symmetry. Sorry, it commutes with this symmetry operator O, because it commutes with this. Because O commutes with the symmetry operator, this also commutes with the symmetry operator, and this has no action. It's in this ground state manifold. It just acts like the identity. Okay, this is really. It's just saying we're in some, like in angular momentum, you'd say that you're in the space of a fixed total angular momentum, and you act with some operator that commutes with all the angular momentum operators. It acts trivially within that space. So this is the identity, and so as a result, this is just psi s again, and we can just factorize this out and write psi of t is proportional to the original psi s and times some phi, which in the environment, which could change in time because, there was a E alpha acting on phi e, because this was S alpha, E alpha. Okay, and so that stuff can just go into some time dependence of this. But here, this is the same state as we started with, so there's no change in the state, there's no decoherence. But now, well, let's see, get rid of this. Okay, but now we can go to second order. Okay. So it's second order. So here, second order, I don't mean second order in time, it's second order perturbation theory in the coupling. So here we have to include, so I look at things which, it's the term that's first order in time, but it includes the virtual process where we've coupled to an excited state and back down to the ground state. So the to second order in time, the second order contribution, which adds on to this, is the piece that's, so it's still the bit that's linear in time, but it's coming from virtual processes where you go to the excited state, which is at some energy, the energy gap. In the model I was looking at, this gap would have been this coupling K, or the bandwidth, or so the band gap. So we have something like this, and then we have the second order process, so I sum over alpha and beta, and now I have projection on the ground state, S alpha, projection on the excited state. Okay, so this is because we're coupling from the ground state to the excited state, acting on psi S, and then we have, times E alpha, E beta acting on the environment. Okay, so this is S squared over energy gap, so it's the second order term. And this, so the action comes from this thing, which I'll call C alpha beta. Involves two of these system operators, alpha and beta. And this, it's straightforward, well, it's straightforward to show that this commutes, it still commutes with the symmetry operator, but it differs from what I said before here. Here, this S commuted with the symmetry operator, but it differs because this is not necessarily a Hermitian operator. So it's, in general, it's non-Hermitian. Okay. So C alpha is, I can write it as some X alpha beta plus I Y alpha beta, where X and Y are Hermitian operators or observables that are acting on the system. They carry two labels, alpha and beta, but because it's a second order process, but anyway, they're just some operators that act in the system. But this thing, it commutes with the symmetry operator, but it has this non-Hermitian part. And then you see that there's actually a difference that emerges, which is that if O is unitary, then the fact that C alpha beta commutes with O means that both X and Y commute with O, and so these operators acting on the system still preserve the symmetry, and in particular this Y alpha beta commutes with the symmetry operator, and this gives rise to, again, we can follow things through, and you can argue that this leads to no decoherence. This just acts as the identity on that space, and we can factorize out the state psi s. But if O is anti-unitary, then, well, I times Y commutes with O, but it means that Y doesn't, because Y anti-commutes with O, actually. So Y alpha beta O is non-zero. Here you do get decoherence. That is that the action of the psi on the state psi mixes the states and changes the qubit from whatever state you started from into something else. So this just to restate that in another way, this, if I look at what this operator y is, just extracting it out from this expression, then essentially y ends up looking like I times, so it's a Hermitian operator, it's I times the commutator of S alpha with S beta divided by the energy gap. Okay, so this is, S's are Hermitian, so this commutator would be anti-Hermitian, but I makes it Hermitian, so this is a Hermitian operator. And this, what's happening is that when you include these virtual processes, you generate operators acting on the system, which are of this form, which do not preserve the symmetry. Okay, so this thing does not, which where y alpha beta, comma O is non-zero. So we started with this assertion that we were going to consider system environment couplings where the operators acting on the system all commuted with the symmetry operator. Well, we can do that at that first order term, but when we go to higher order, we find that we get actions, or we generate actions, operators acting on the system which do not preserve that symmetry. And that's for the reason, that comes down to the reason I said before, that this notion that we can factorize that symmetry between system and environment is flawed. We can factorize it for our initial Hamiltonian, but the actual effect when we consider the time evolution is that we generate effects of this type. And just to, in the case, to make that explicit, in the case that I was considering, or that I motivated this with, where I had this peculiar extended SSH chain, we could have some chain like this, and then we could say that, well, we're going to, just as I put in noise on the couplings between here and here, we can imagine that our couplings, that coupled to the environment could be an operator, our operator S1 could be the hopping between here, and our operator S2 could be the hopping between B and A. Now, those are operators which preserve the chiral symmetry because they're off diagonal, but we can take these operators and compute and see what this y is. So here, S1 would be some magnitude times, well, I have to label these sites. So this, if this first unit cell is 0 and the second unit cell is 1, then I write this as something where I create a particle. No, let me just follow it. So I create a particle on the A site of the 0th unit cell and destroy a particle on the B site of the 0th unit cell, plus Hermitian conjugate, and S2. There's some amplitude, and then I have I create B and 0, and I destroy A and 1, plus the Hermitian conjugate. And you can then compute, the y 2 from the commutator, S1, S2 over whatever energy gap squared. It will generate terms which are of the form CA0, CA1, sorry, there was an I here, plus Hermitian conjugate. So it generates hoppings that actually directly couple A to A, and this is a term that violates this chiral sublattice symmetry because it has a direct connection between the A sites. So you can very explicitly see how this, once you go to higher order, you violate the symmetry, and that violation will lead to decoherence. Okay, so let me just conclude by just saying the consequences again, that the surface states protected by anti-unitary symmetry will decohere. So if this is even, we have a system, let's say it's coupled to a bath at thermal equilibrium. If that bath is at a temperature which is non-zero, and it couples in the way I said, of just through operators that preserve the symmetries, but it's fluctuating in time because at non-zero temperature, it's non-zero temperature, and therefore can exchange energy with the bath. Then the system will decohere, and the decoherence rate gamma it falls to zero as temperature goes to zero. The power law. So it falls as some power law, where the power law, as usual, depends on the spectral function or the spectral density of the bath. So we study this in sort of Caldera-Leggett type model, and of course the exponent here falls like that. But more generally, it also falls like a power law in the energy gap. It's some exponent which also depends on the spectral function of the bath. So it will decohere, and the point is even for symmetry preserving couplings. So this you should contrast with, if the unitary case, for unitary, the decoherence rate is typically falls like exponentially. It's exponentially suppressed. The only way to get the decoherence is to thermally excite into the above the gap, and so there's some decoherence rate for a system at finite temperature there, but it's exponentially suppressed as opposed to power law suppressed. So this this is very general result, but of course it only applies in cases where you have this anti-unitary symmetry protection. So the cases where that's relevant are a subset of all possible topological phases. So they're not everything is destroyed by this, far from it, but the sorts of cases you could consider are the spin-a-half edge states of the Haldane phase of a spin-1 chain. So if you couple even to energy density, your couplings don't break time reversal symmetry. If this is protected by time reversal symmetry and time reversal symmetry alone, then you expect a decoherence that falls as a power law, or this the Z2 topological insulator. That's the quantum spin Hall, where we have a two-dimensional system carrying these helical edge states where there's a time-reversed partner of states going the other direction. Then this provides another mechanism by which coupling to a thermal bath can cause backscattering of these edge states at non-zero temperature. But other cases are not influenced. The quantum Hall effect is not. It's not protected by time reversal symmetry, or this Majorana states in spin polarized fermions are also not subjected to this, and they're protected by unitary symmetry, so they're suppressed only exponentially. Okay, well that brings me to the end of everything I wanted to say. Maybe I just make a couple of concluding remarks about the lectures. So I've tried to give an overview of some general aspects of quantum dynamics and topology, focusing on symmetry-protected phases. And almost everything I said was about free fermions and translational invariance, really just try and get across things as simply as possible in these intuitive pictures. Some of the results I stated are restricted to free fermions and translational invariance, but many of them are not. So in particular, everything I said today about decoherence and anti-unitary symmetries, the topological classification, all of that can carry through to interacting systems also in the presence of disorder. So that's robust. But there are many things, of course, I haven't been able to say about interactions, many-body localization, non-Hermitian topology, which is something that's very active and very interesting, not just in quantum systems, but also in classical systems, and also in these open systems, thinking about density operators and how one classifies topology. So there's much is understood about those as well. There's much more left to understand, and I hope that this has given an introduction to at least some of the background so that you can explore what the open questions are based on the little bit of understanding I tried to convey here. But I'll stop here and thank you for your attention.
All right, thank you very much. So are there questions? Okay, well, maybe I can start with one. So since you mentioned non-Hermitian topology, so I mean, could you? I mean, is there a connection with what you just discussed here? With
so I missed the, what
a connection between a non-Hermitian topology, which you mentioned.
so yeah, so non-Hermitian. So the connection. The connection that that we explored, the closest connection that I know is, so everything I've been saying here is about quantum many-body states, and actually to connect that to non-Hermitian topology either requires some approximation, that you neglect some jump operators or neglect quantum jumps and therefore derive some effective non-Hermitian dynamics for the quantum system, or you consider classical systems. So much of the non-Hermitian topology is directly related to classical systems. But there's one very interesting way in which you can make a connection, which is work that I was involved in with Simon Liu, and this makes use of a mapping or representation due to Prozin, which showed that if you have master equations, so an open system, you can write the master equation in the Lindblad form. You have an equation for the density operator, and if you're dealing with free fermions and the jump operators there are linear in the fermions, then the master equation is a quadratic, can be written as a quadratic form acting on the fermions. And in fact, as Prozin showed, the master equation itself can be written as a non-Hermitian Hamiltonian, or you can view it as a non-Hermitian Hamiltonian. So there's a nice connection, which is that you can use the topological classification of the non-Hermitian matrices to say something about the spectrum, or the dynamical spectrum of the master equation for these free fermion systems. And it turns out that there are connections, well, to the Altman-Zernbauer symmetry classes, and you can see what the fate is of the gapless modes and the topological phases, how those translate into features in the spectrum of this master equation. So there, I think that the connection is through that to use results of the non-Hermitian topological classification to think about master equations for open systems where that non-Hermitian structure emerges naturally.
Thank you. Other questions? In the chat, maybe? No.
So in the end, this when you have a anti-unitary symmetry, this is for in some sense is a symmetry, in some other sense is not a symmetry, right? We call time reversal and charge conjugation symmetries, but because they are not implemented as a unitary operator, there are some differences.
There are, well, so here there are clearly differences. Yeah, in this. Here we're looking at dynamical effects. Also, how entanglement grows, dynamics under time evolution, and there it's clear that because time reversal and anything that's anti-unitary behaves in a special way under time evolution. That's the so I would say that the difference is emerging because we're asking questions here which are about time evolution or entanglement growth, and those anti-unitary symmetries clearly have a very different character when one asks about such properties.
Okay, thank you.
Other questions? Well, so if not, then let's thank Professor Cooper again for this nice series of lectures.